Hi, this is Dr. Divya from United Group of Institutions, Allahabad. I welcome you all to this third session of molecular orbital theory. Basically, it is related to the main topic, chemical bonding. Assuming now that you have understood the process of formation of bonding and anti-bonding molecular orbitals, the postulates of molecular orbital theory, and the molecular orbital diagrams for various homonuclear diatomic molecules, along with the calculation of bond order, today we have the following lecture agenda. You can see here that this lecture would contain molecular orbital diagrams for various heteronuclear diatomic molecules. Amongst various heteronuclear diatomic molecules, it may be nitric oxide, NO, CN, and then CO. Along with that, we can cover hydrogen fluoride, HF molecule. So, related to these molecular orbital diagrams, we would try to cover some questions and answers. Apart from that, at the end, we would be taking an overview of the entire session. So, in continuation to our previous two sessions, let us come to the first and the third session, which is related to the formation of molecular orbital diagrams for heteronuclear diatomic molecules. So, students, let us start with two questions first. You can see that this question states that with the help of molecular orbital diagram, explain why hydrogen forms diatomic molecule while helium remains monoatomic. So, here I think I am very much sure that you are aware of the fact that we have to calculate the bond order in this particular case. So, when we calculate the bond order, we understand that in case of hydrogen, the bond order is 1, while in case of helium molecule, it comes out to be 0. So, the one hydrogen molecule atom combines with the another hydrogen atom to form hydrogen molecule with the bond order 1, which shows that there is a stable bond formation. What does this mean? That two hydrogen atoms combine together to form the hydrogen molecule. It is a stable molecule, and you can see that there is a single covalent bond between two hydrogen atoms. These are two hydrogen atoms and a single covalent bond is formed here. Now, when we consider helium molecule, we are also aware of the fact that in this particular case, the bond order is 0, which shows that this species does not exist, right. So, helium remains monoatomic. Monoatomic means it does not form diatomic molecule, while hydrogen is diatomic molecule because both the hydrogen atoms combine to form a stable hydrogen molecule. So, this is the answer to this first question. Second, explain why nitrogen has higher bond dissociation energy than N2 plus, while O2 has lower bond dissociation energy than O2 plus. This question was also discussed in the previous session, but here we are going to take a revision of that. So, here this table already suggests that in case of nitrogen, you can see that the bond order is 3. Here the bond order is 3, but in case of N2 plus, it is 2.5. So, what does this mean? That since all of us know that bond order is directly proportional to the bond energy, that is bond dissociation energy. So, if the bond order of N2 is greater than that of N2 plus, obviously it has higher bond dissociation energy than N2 plus. Similarly, in case of N2 plus, you can see that it is higher as compared to O2. So, here it is clear that why O2 plus has higher bond dissociation energy as compared to O2. So, this is the basic difference that we have already seen while discussing the molecular orbital diagrams for various homonuclear diatomic molecules. So, let us come to the molecular orbital diagrams for heteronuclear diatomic molecules. So, here what do we see? When we talk about heteronuclear diatomic molecules, then it means we are going to consider two different atoms. Two different atoms here means their electronegativities are different, right. So, the energy levels of the atomic orbitals of more electronegative element must be slightly lower. Here in the second point, it has been mentioned that when two atoms are having different electronegativities, then obviously the atomic orbital of the more electronegative atom would be a little lower. Its position would be slightly lower. Now, the electrons in the bonding molecular orbitals will come closer, will be nearer to the more electronegative atom, whereas the electrons in antibonding molecular orbitals will be nearer to the less electronegative atom. How is this possible? We will go ahead and see that how it happens when we will draw the molecular orbital diagram for heteronuclear diatomic molecules. So, students, you can see here, this is the molecular orbital diagram for NO, or even you can consider CN. So, when we write down the electronic configuration for both the atoms, nitrogen and oxygen, so the electronic configuration for nitrogen is 1s2, 2s2, 2p3, right. So, when we are considering NO molecule, then another atom is oxygen, 1s2, 2s2, 2p4, right. So, when we are going to draw the molecular orbital diagram for NO molecule, then what will happen? Yes, we can see the difference in electronegativities. Which one has higher electronegativity? Obviously, oxygen has higher electronegativity. So, we can see here that the energy level of oxygen atom, the atomic orbital of oxygen atom, is slightly lower as compared to the energy level of nitrogen or any other atom which has lesser electronegativity as compared to the oxygen atom, or any other atom having more electronegativity. So, here there is a difference in the levels of energies of atomic orbitals. So, in this way an unsymmetrical diagram will be created. Now, what do we mean by the third point which we have mentioned while discussing the formation of molecular orbital diagrams for heteronuclear diatomic molecules? The bonding molecular orbital which will be formed here would be closer to the more electronegative atom, while anti-bonding molecular orbital would be closer or nearer to the lesser electronegative atom. In this way, all the molecular orbitals will come along the same line. So, friends, today you can see that in case of NO molecule, we have drawn this diagram. Now, here the order you can see is 2 1 2 1, while it can be 1 2 2 1, because it hardly matters. It does not affect the properties of the molecule. So, whenever I teach my students, I do consider the 1 2 2 1 model only, 1 2 2 1 configuration only. Why? Because the number of electrons is obviously greater than 14. If it is 14 or more than 14, then we consider the electronic configuration or the order of energies of molecular orbitals of the first category, which is of heavier elements. So, we can keep it like this, like sigma 2 pz and then pi 2 px and pi 2 py and so on. So, it hardly matters. So, we are going to consider this one as well. So, here you can see that when we try to find out the bond order, then bond order obviously we can calculate with the same formula, 1 by 2 number of electrons in bonding minus number of electrons in anti-bonding molecular orbital, then its bond order is 2.5. So, when we come to the properties of NO, then we can conclude that it is paramagnetic in character. Why? Because there is one unpaired electron present in the molecular orbital diagram or electronic configuration of NO molecule. Similarly, its bond order is 2.5. In case of CN also, we can consider the same flow of energies. Now, let us move ahead when we consider carbon monoxide, CO. Yes, this is a special case, this is an exceptional case wherein there is mixing of atomic orbitals or the molecular orbitals. Why? Because we can see that there is a big difference in electronegativities of both the atoms, carbon and oxygen. Oxygen and carbon, there is a big gap in electronegativities. Oxygen is much more electronegative than carbon, and that is why you can see that their levels differ a lot. The atomic orbital of oxygen atom is here, while that of carbon atom is here. So, in this way you can see the big gap. Now, due to this big gap, you can see that when the p orbitals enter into the process of overlapping, so this sigma 2 pz and pi 2 px and pi 2 py come inside this, and then the order flow is like this. So, this is how we can see that due to mixing of molecular orbitals, there is a little difference in the electronic configuration. So, when we write down the electronic configuration of carbon monoxide molecule, you can see if you leave Kk shell, completely packed shell Kk, so the first energy level, then we can start from here, sigma 2s2, sigma star 2s2, then pi 2px2, pi 2py2, then sigma to pz2, finally pi star to px and pi star to py, and so on. So in this way, bond order, when we calculate, it comes out to be 3. So this type of molecular orbital diagram actually explains all the properties of carbon monoxide molecule. So this was the hypothetical molecular orbital diagram, but it is very well accepted. It is very much in agreement with all the properties that were experimentally identified and defined by spectroscopic techniques. So this is how we can see the difference between the molecular orbital diagram of NO and CO molecule. Now this is another example that we should consider, hydrogen fluoride molecule. So here also we can see that there is a big difference of electronegativity between both the overlapping atoms. One is hydrogen atom and the other is fluorine atom, highly electronegative element, right. So when we write down the electronic configuration of hydrogen, it is 1s1. There is only one s orbital containing only one electron. While in case of fluorine, when we write down its electronic configuration, 1s2, 2s2, 2p5, right. Now the question arises, 1s orbital will overlap with which orbital of fluorine atom? Because we all know the conditions for the combination or the overlapping of atomic orbitals. Number 1, the energies of the overlapping atomic orbitals must be the same. Number 2, symmetries must remain the same. So if we think that s and s atomic orbitals are having the same energy, so they should overlap, but this does not happen in this particular case. The energy difference lies between the 1s of hydrogen atom and 1s of fluorine atom. Similarly, there is an energy gap between 1s of hydrogen atom and 2s of fluorine atom. What we can see here is, if this is 2s, you can see that 2s and 1s, there is a big gap. Similarly, there must be 1s as well, 1s of fluorine atom as well. So 1s is low lying energy orbital. That is why we cannot consider 1s or 2s to be overlapped with 1s of hydrogen atom. So what is the other option left? We can see that yes, 1s of hydrogen atom and 2p of fluorine atoms come closer, come at the same level, approximately the same level, so that they can enter into the process of overlapping. Now this is also very much clear to all of us that yes, p and s overlap is also possible. If we consider pz present as along the molecular axis, then we can explain, we can consider the process of overlapping of s with pz orbital. So here you can see that if there are px, py and pz, 2px, 2py and 2pz of fluorine atom, then pz and s combine together, overlap together to form, this is sigma spz, and this is sigma star spz. Now what about this? This fluorine 2px and fluorine 2py remain at the same energy level. This is fluorine 2px and fluorine 2py. What about this? This is also fluorines 2s, right. Similarly, there might be fluorines 1s, right. So 1s2, 2s2, and here total number of electrons is 1, 2, 3, 4, 5 plus 1, 6. So 6 electrons are to be filled in here. So we start filling the molecular orbitals from here. So 1, 2, 3, 4, 5, 6. Now always remember that these px and py molecular orbitals, these are not the molecular orbitals, these are actually the non-bonding orbitals of fluorine atom, which remain at the same energy level. So whenever we write the electronic configuration for HF molecule, how do we write? Let us try to understand. This is fluorine 1s2, right, and again fluorine 2s2, right, which remain unaffected. Then sigma spz, sigma spz2, and then comes fluorine 2px2 and fluorine 2py2. So fluorine 2px2 and fluorine 2py2, right. And this way finally we get sigma star spz 0. So even this can also be considered sigma star spz 0. It may be omitted, but here I have written. Now, if we try to find out the bond order, how we can calculate bond order is equal to 1 by 2. Now, what the students commit the mistake, they consider this also as the bonding or anti-bonding molecular orbitals or the electrons, but we have to consider only the bonding and anti-bonding molecular orbital. So, there is only one bonding molecular orbital, that is sigma sp(z). So, the number of electrons present in bonding molecular orbital is 2. So, this is 2, and number of electrons present in anti-bonding molecular orbital, it is 0. So, 0. So, what is the bond order? 1. What does this indicate? This indicates that yes, HF is a stable molecule. This is a stable molecule, right, and there is a single covalent bond between hydrogen and fluorine atom. In this way, we can see that in case of heteronuclear diatomic molecules, we have considered 3 examples: NO, CN, both are having the similar type of molecular orbital diagram. Then CO. CO is having an exceptional case wherein there is mixing of molecular orbitals, and then HF. This is also another typical case wherein we have considered the formation of molecular orbitals and then calculation of bond order. In all these cases, the diagrams are unsymmetrical because of the differences in their electronegativities, right. So, today let us come to some questions. If we ask you to calculate the bond order of HF, always remember that you have to consider only the bonding and anti-bonding molecular orbitals and never the non-bonding molecular orbitals that you usually consider. So, the bond order in case of HF molecule is 1 only, that we have written here. Now, whenever you are asked to arrange the species, ionic species, in the increasing or even decreasing order of their stability or bond dissociation energy, then always remember you will have to find out the bond orders. On the basis of bond orders, you can easily categorize and arrange the elements or the ionic species into different orders as asked by the examiner or someone. So, here you can see O2 has 2 bond order, O2 plus has 2.5, so it has higher bond dissociation energy, and so on. You can calculate the bond order and you can arrange the species in the increasing or even decreasing order of their stability or bond dissociation energy. And also we have understood that bond dissociation energy is inversely proportional to the bond length. So, here the reverse order is given whenever the level of or the increasing or decreasing order of bond lengths is being observed. So, here you can see that N2, N2 plus and N2 minus, the bond order is like this. So, in that way you can arrange different species in the increasing or decreasing order of their bond lengths. Between NO and NO plus, which one is diamagnetic and which one is paramagnetic? This is also a very important question, because whenever we draw the molecular orbital diagram of NO, you can easily calculate the bond order you have calculated, but it depends upon the number of unpaired electrons, presence or absence of unpaired electrons. If you go through the molecular orbital diagram, you will see that in case of NO, there is one unpaired electron present. That is why NO is paramagnetic. But when NO plus is formed, then what is happening? We are removing one electron, there is only one unpaired electron which is being removed, and therefore NO plus becomes diamagnetic. So, between NO and NO plus, which one is diamagnetic and paramagnetic? You can easily say that NO is paramagnetic while NO plus is diamagnetic. So, dear students, in continuation to the molecular orbital diagrams for homonuclear diatomic molecules, we have studied today the formation of heteronuclear diatomic molecules and also their molecular orbital diagrams. Also, depending upon their bond orders, we have defined their characteristics, the electronic configurations of various heteronuclear diatomic molecules. In the next session, we will try to understand the concept of band theory of metals, the theory, the molecular orbital theory, which is extended to solids. As of now, thank you very much. See you in the next session of chemical bonding, which is related to band theory of metals. Thank you. Wish you all the best.